Have you ever felt like you're holding, I don't know, a map to this huge, complex landscape of information, but you're just not sure where to start digging for the real treasures?
Yeah, I know that feeling.
Well, today we're basically handing you the compass and the magnifying glass.
That's a good way to put it. We're embarking on a deep dive into an incredibly comprehensive guide today, the SQL Server 2012 Bible.
Right.
And this isn't just, a rehash of the official docs. It's really a guide that tries to walk you through the critical concepts, real-world examples, best practices, kind of like a friend helping you get up to speed.
Our mission here is pretty simple, really. We want to pull out the most crucial insights, maybe some surprising facts, and the really practical takeaways from this, massive guide.
It is pretty massive.
Yeah. We want to help you become truly well-informed on SQL Server 2012, get you to that aha moment without feeling, totally overwhelmed. Think of it like a shortcut to really getting this powerful database system.
Absolutely.
Yeah.
And a major theme running through the material for SQL Server 2012 is definitely its focus on enterprise-level excellence. This version was really engineered to enable more scalable, more robust systems.
Okay, so if we're building these big, powerful systems, what's the actual, heart of SQL Server? What's that foundational piece?
Well, at its core, SQL Server revolves around the database engine. You'll often hear it called the relational engine.
Mm-hmm.
That's the component doing all the heavy lifting for relational database work. But it's part of a bigger picture, right? SQL Server also includes a whole suite of services, things like business intelligence tools.
Ah, BI stuff.
Exactly, like OLAP for multidimensional databases and data mining for finding patterns, plus various cloud functionalities we're starting to come in.
That sounds like a lot of moving parts. And speaking of how companies actually use this, one really significant shift highlighted in the material was around the SQL Server 2012 editions, and maybe even more surprisingly, the licensing. What changed there?
Right, that was a big one. So the main editions were kind of streamlined down to 3. Enterprise, which was for your mission-critical stuff, big data warehousing.
The top tier.
Yeah. Then business intelligence, that was actually a new edition, bringing in premium corporate and self-service BI features.
Yeah.
And then standard.
Okay.
But the really impactful change, the one that made people sit up, was the shift from per-socket licensing to core-based licensing.
Right. And this is where it gets really interesting. If you were involved in budgeting or planning infrastructure back then.
Oh, yeah.
If you had, say, a server with 2 quad-core processors running SQL Server 2008 R2, you only needed 2 processor licenses. Simple. One for each chip.
Mm-hmm.
But then, boom, SQL Server 2012 comes along, and that same server suddenly needed 8 licenses. Because every single core needed licensing.
Exactly. 8 cores, 8 licenses.
That's a huge jump. A pretty dramatic cost increase and planning headache for a lot of companies, wasn't it?
It absolutely was a significant shift, yeah. And it definitely caught many people off guard. Beyond licensing, when you're actually installing it, there are all the usual planning things to think about: hardware, software requirements, patching strategies, firewall config.
Sure, the base.
But one key architectural concept the material highlights is default versus named instances. You can only have one default instance of SQL Server per computer, but you can stack up multiple named instances on the same machine.
Ah, okay. So you could have SQL prod and SQL dev on the same box.
Precisely. Gives you great flexibility for resource segmentation or testing.
That makes sense. So, okay, SQL Server is up and running. How does it typically talk to client applications or other services?
Well, the default way clients connect is usually over a TCP/IP using port 1433. That's the standard listener port.
Got it.
And for developers wanting to leverage the new features in 2012, the key was the SQL Server Native Client, or SNAC. That was the gateway, offering things like improved metadata discovery and, importantly, better diagnostic info if connections started failing.
Okay, so moving beyond just the technical setup, a huge emphasis in our material is placed on this philosophy of smart database design. It's presented not just as a good idea, but as the absolute foundation for a performance system. What's the core idea behind this elegant physical schema they talk about?
Exactly. The argument is really strong here. An elegant physical schema directly leads to great set-based queries.
Set-based, okay.
Right, which then allows for good indexing, and that, in turn, results in short, tight transactions. And it's this whole chain reaction that boosts concurrency and scalability. It's all about building it right from the start, rather than trying to tune your way out of a bad design later.
It sounds like laying a really solid foundation. And the material even gives a kind of blueprint for measuring how healthy a database is, defining these 6 key attributes under what they call the information architecture principle.
Yeah, those attributes are usability, extensibility, which is basically how easily it can adapt to new requirements.
Future-proofing it.
Kind of, yeah. Then data integrity, performance, availability, and security. All crucial, but if you don't nail data integrity, the others can become pretty shaky.
And this is where we hit a real aha moment in the material, especially around data integrity. There's this great little anecdote about a database developer, Audrey Hammonds.
Oh, I remember this one.
Yeah. She apparently volunteered to stop writing COBOL, which, let's be honest, many developers might relate to.
Fair enough.
And she became totally convinced that the world would be a better place if people would stop, relax, enjoy the view, and normalize their data. Why is normalization so transformative? Why does she feel that strongly?
It's such a powerful statement, isn't it? Because normalization really at its heart is about reducing redundant data, cutting down on repetition, and crucially, preventing these things called modification anomalies.
Modification anomalies.
Yeah.
What does that mean in practice?
Well, think about the headaches you avoid when you only have to update a piece of data in one place. Let's say you have a customer's address stored in 5 different tables. If they move and you miss updating one of those tables.
Inconsistency, bad data.
Exactly. Normalization helps ensure that data lives in one logical place, so updates are clean and consistent. While the specific normal forms, first, second, third normal form, can get a bit academic.
Right, they can.
The core idea is simplifying maintenance and boosting data consistency, reducing that redundancy. First normal form, for example, just means no repeating groups, like don't have phone 1, phone 2, phone 3 columns, put them in a separate related table. Second normal form is about making sure attributes depend on the whole primary key. Simple ideas, big impact.
So it's about stopping data from getting out of sync with itself. And underpinning all this integrity talk, the material hammers home the AC properties of transactions: atomic, consistent, isolated, durable. What's the real-world consequence if a database doesn't strictly follow ACID?
Oh, they're absolutely fundamental. The bedrock. Imagine a world without ACID. Your online bank transfer might take money out of your account, but never put it into the other account.
Yikes.
Or an inventory update could leave your stock levels completely messed up across different parts of the system. AC ensures these critical operations are all or nothing. They either complete fully and correctly, or they're rolled back entirely as if they never happened. It prevents those real-world business nightmares and maintains what they call transactional integrity.
That makes total sense. It's the guarantee. So beyond individual data points being correct, it's also vital how they relate to each other. We're talking relationships, like one-to-many. Like one customer can have many orders.
Right. Or one order can have many order detail lines. That's a classic one-to-many.
And then you have one-to-one, less common maybe, and many-to-many, which usually need that extra table in the middle, right? Like students and courses.
Exactly. An intermediary or linking table. And once you have that solid relational design figured out, then indexing becomes absolutely key. Indexes are essentially, organized pointers. Shortcuts for the database to find data fast without scanning whole tables.
Okay.
Without a good design and effective indexing, you inevitably run into locking and blocking issues. Basically, queries getting stuck waiting for each other, and these are major performance killers.
The material really stresses this. Performance tuning can't magically fix a fundamentally flawed database design. It's a chain of dependencies.
It really is like building a house, isn't it?
Yeah.
A shaky foundation means cracks appear everywhere else, no matter how nice the paint job is.
That's a great analogy.
This also reminds me of development methodologies. The material briefly touches on the contrast between the traditional waterfall process, gather all requirements up front, design, build, test.
Right, the rigid steps. Yeah. Versus agile development, which is all about shorter cycles, iterations, getting user feedback constantly, because let's face it, users often don't really know what they want until they see something working.
So true. Agile embraces that change.
All right, let's pivot a bit and talk about the language itself. T-SQL. It's described rather poetically in the material as the romance language of data.
Trickles like that.
And more technically, as a declarative language. What's the real significance of calling it declarative?
That's a really crucial distinction. Declarative means you tell the database what result you want, not how to go about getting it. You declare the desired state.
Okay, so I say, give me all customers in California, not scan the customer table, check the state column for CA, put those rows in a temp table.
Exactly. You don't specify this step-by-step execution plan. The database engine's query optimizer figures out the most efficient how based on statistics, indexes, and all sorts of internal magic.
Got it.
And when it comes to the select statement, the workhorse of querying, there's that surprising logical processing order. You write the clauses in one order, select, from, where, group by, having, order by.
The standard syntax order.
Right. But the database engine actually processes them differently behind the scenes. It starts with from and joins to figure out the source data, then applies the where clause to filter rows, then group by, then having to filter groups, then select to determine the final columns, and usually order by comes very late in the process to sort the final result.
That logical order is so fundamental for understanding performance, isn't it? Thinking about when filters get applied.
Absolutely. It affects everything.
And speaking of performance, what were some key best practices highlighted for writing good T-SQL?
Well, two big ones jump out. First, always use qualified names. Schema.objectName, like Debo.customers instead of just customers. This helps SQL Server reuse execution plans more effectively, which is a big performance win.
Okay. Consistency helps cache.
Right. And second, this is a super common mistake. Always let the database engine do the work of restricting the rows returned. Use specific where clauses. Don't pull back like a million rows to your application and then filter them there. That's incredibly inefficient. Filter close to the data.
Push the filtering down to the server. Makes sense.
Yeah.
Okay, moving on to working with strings. T-SQL has a ton of functions for chopping them up, putting them together, concat, format, left, right, len, trim.
All the usual suspects.
Replace.
Yeah.
Yeah.
But beyond those, the material points out a funny little quirk, something that can really trip you up if you're not expecting it. What's that surprising detail?
Ah, yes, the single quote. The surprising fact is how you actually get a single quote into a string, literal, in SQL Server. You have to use two single quotes back to back.
Right. So if you want the string life's great,
Yeah.
you actually write it as life's great.
Exactly. That first quote starts the string, the double quote is interpreted as a single literal quote inside the string, and the final quote ends the string. It looks weird, but it's the rule. Forget that, and your query breaks. Oh, I've definitely wasted time debugging because of that one. It's always the little things.
Always. The material also mentions functions like soundx and difference for phonetic matching, finding names that sound similar even if they're spelled differently. Useful sometimes.
Yeah.
But there's a caution. Soundx in particular can be a performance hog if you're not careful, because it often must execute for every row in your query. It can prevent the optimizer from using indexes efficiently on that column. So use with care, especially on large tables.
Good warning. Okay, so once you've got your design solid and you're writing decent T-SQL, the real power often comes from combining data across different tables, right? And that's where joins come in. Can you quickly walk us through the main types again?
Sure. Joins basically combine data horizontally, sticking columns from different tables together based on related values. The most common is the inner join. It only gives you rows where there's a match in both tables.
Only the intersection.
Right. Then you have outer joins. Left outer join keeps all rows from the left table and matching rows from the right. If there's no match on the right, you get nulls. Right outer join is the opposite, keeps all from the right. And full outer join keeps all rows from both tables, filling in nulls where matches don't exist on either side.
Okay, covers all bases.
Pretty much. There are also less common types like cross join, Cartesian product, every row from one table combined with every row from the other, usually accidental, and theta joins based on conditions other than equality, like greater than.
And what about combining data vertically? Stacking results.
Ah, right. That's where the union operators come in. Union all is the simplest. It just takes the results of two compatible queries and sticks them together, duplicates and all.
Just appends them.
Yeah. Union without the all does the same, but also removes duplicate rows, which takes a bit more work. Then you have intersect, which finds only the rows that appear in both result sets, and except, or difference, which finds rows that are in the first result set, but not in the second. So vertical comparisons.
Got it. Horizontal with joins, vertical with unions intersect except. And for writing really complex queries, what advanced techniques did the material highlight?
Well, common table expressions, or CTEs, are fantastic. Think of them as named, temporary result sets that you define at the start of your query using a with clause. You can then refer to that CTE name later in the main query, even multiple times. They make really complex logic much easier to read and manage compared to nested subqueries or lots of temp tables.
Like building blocks for your query.
Exactly. And then there are the windowing and ranking functions. These are incredibly powerful. Functions like row number, rank, denser rank, and aggregate functions used with an over clause, like sum, over partition by, order by when.
What do those let you do?
They let you perform calculations across a set of table rows that are somehow related to the current row of the window. So you can easily calculate things like running totals, rankings within categories, or percentages of a group total, all without complex self-joins.
Very cool. Like analytics built right into the query.
Pretty much. And SQL Server 2012 specifically added the offset and fetch arguments to the order by clause. This makes implementing efficient server-side paging, show me rows 11 through 20, much, much simpler and cleaner than older methods. Huge win for UI development.
Definitely useful. Okay, let's talk about views. They're often called virtual tables, but the material is quick to point out they're really nothing more than stored T-SQL select queries. They don't hold data themselves, usually.
That's correct, most of the time. A standard view is just a saved query definition. When you query the view, SQL Server runs the underlying select statement. They don't store data unless they are specifically indexed views, sometimes called materialized views.
Ah, okay. So an indexed view does store the results.
Yes. Creating a clustered index on a view physically stores the results set, like a table. It pre-computes the data for faster access, but it comes with overhead for maintaining that stored data when the underlying tables change.
Gotcha. So what are the main benefits of using standard non-indexed views?
Several benefits. They can simplify complex database schemas for users or applications, hiding complicated joins or calculations behind a simple interface. They can be used for security, exposing only certain columns or rows from a table, or they can even consolidate data from multiple tables or even multiple servers into a single logical view.
Handy for abstraction, but there's a cautionary tale mentioned too. Views can sometimes be performance killers. And what's this risky with encryption option?
Right. If the underlying query in the view is inefficient, or if the view prevents the optimizer from using good indexes on the base tables, then querying the view can be slow. You still need to understand the underlying query. And the with encryption option, well, it scrambles the view's definition text in the system tables.
So you can't see the T-SQL code anymore.
Exactly. You can't easily script it out using Management Studio or query the system views to see the code. While it might seem like a security feature, the material warns it can cause major headaches later if you need to modify or debug that view and the original script is lost. You basically lock yourself out of easily seeing your own code. It's generally discouraged unless there's a very specific, compelling reason.
Yeah, sounds like a potential trap. Okay, finally, on the T-SQL front, let's talk about modifying data. Insert, update, delete. The material really hammers home the idea of thinking set-based here too, not row by row.
Absolutely. Relational databases are optimized for operating on sets of rows. For insert, you've got flexibility. You can insert explicit values using values. You can insert the results of a select statement. You can even execute a stored procedure and insert its results into a table using insert.exe. And there's the handy select.into syntax to quickly create a new table based on a query result.
Lots of ways to get data in. What about update and delete?
Similar set-based thinking applies. You use a where clause to specify which set of rows to modify or delete. And importantly, both update and delete statements in SQL Server can use a from clause. This lets you join the target table to other tables to help determine which rows need updating or deleting based on conditions in those related tables. Very powerful.
Okay, joining even in updates and deletes. Cool. And then there's the command described as a superpower, merge. What makes it so special?
Merge really is impressive. It lets you perform insert, update, and delete operations in a single statement based on whether rows from a source match rows in a target table.
All three DML operations in one go.
Yes. You specify the source and target, the join condition, and then you have clauses like when matched, then update. When not matched by target, then insert. And when not matched by source, then delete.
Wow. Can you give an example?
The classic example is synchronizing data, like maybe updating a product list based on a feed, or the flight manifest example mentioned. You merge the incoming flight data with the current manifest. If a passenger exists, matched, update their seat assignment. If they're new, not matched by target, insert them. If someone on the manifest isn't in the incoming data, not matched by source, maybe delete them or mark them as inactive. It avoids multiple separate insert, update, delete statements, reducing round trips and potential locking conflicts. It's incredibly efficient for those kinds of synchronization or upsert tasks.
That sounds incredibly useful for ETL or data integration.
It really is. And one more thing with DML, the output clause. You can add an output clause to insert, update, delete, and merge statements to capture information about the rows that were affected by the operation, like the inserted IDs or the before and after values of updated columns, often into a table variable or temp table. Very handy for auditing or feeding downstream processes.
Nice. Capturing the changes as they happen. So tying this all together, we circle back to transaction control and error handling. We mentioned ACID earlier, and for handling errors gracefully in T-SQL code, the material highlights try-catch blocks.
Yes, standard structured error handling. Just like in many other programming languages, you put the code that might fail inside the try-y block, and if an error occurs, control jumps to the catch block where you can handle it, log it, maybe try something else, or rethrow the error.
And within the catch block, you can use commands like razor or newer in 2012, throw.
Right. Throw is generally simpler and preferred in newer versions for just re-raising the original error. Razor is older but has some unique capabilities, particularly the option mentioned to easily log the error to the Windows application event log and the SQL Server event log using specific arguments. This is super helpful for system administrators monitoring server health, providing clear visibility into application-level errors right alongside system events.
Ah, okay, so Razor has that handy logging integration. Good to know. All right, let's shift gears into some more advanced management topics. The material discusses handling hierarchical data. SQL Server 2012 actually introduced a specific data type for this, hierarchy ID. What does that really mean for developers dealing with things like org charts or product categories?
It's a really interesting data type. It essentially stores the position of a node within a tree structure in a very compact and efficient binary format. So for things like organizational charts, genealogical data, family trees, or manufacturing bills and material parts explosions, the hierarchy ID data type lets you represent these tree-like structures naturally within the database.
Okay, but how does it help? What can you do with it?
Well, because it encodes the path or position, it makes certain types of hierarchical queries incredibly efficient. Things like find all subordinates of this manager, find the level of this employee in the hierarchy, or find the common ancestor of these two nodes. Queries that can be really complex and slow using traditional self-joins or recursive CTEs can often be done very efficiently with the built-in methods of the hierarchy ID type. The material positions it as generally more efficient and performant for these tasks than alternatives like storing paths as strings or using XML.
Wow, so it's like a specialized tool built right in for tree data. Sounds like a game changer if you work with that kind of structure often.
It definitely can be a real performance booster for those specific scenarios.
What about connecting to data outside the current SQL Server instance? How do you handle that?
That's where distributed queries come into play. And the primary mechanism mentioned is linked servers. This lets you configure one SQL Server instance to connect to another SQL Server instance, or even to other data sources like Oracle, DB2, or sometimes even things like Excel spreadsheets or Access databases using OLEDB providers.
So you can query a table on another server as if it were local.
Pretty much, yeah. You use a four-part name like server name.database name.schema name.table name. It allows for one-way communication, letting your local server pull data from or push data to the remote source.
Okay. But what about transactions that span multiple servers? If I need to update data on server A and server B and ensure it either succeeds on both or fails on both?
For that level of coordination, you need the Distributed Transaction Coordinator, or DTC. It's a Windows service that coordinates transactions spanning multiple resource managers, like 2 different SQL servers. It uses a protocol called two-phase commit to ensure that all participants in the distributed transaction either commit the change or roll it back, maintaining data consistency across all the involved systems. DTC configuration can sometimes be tricky, especially with firewalls, but it's essential for those kinds of multi-server atomic operations.
Got it. DTC for the cross-server consistency. Now, shifting to maybe the unsung heroes of database administration, maintenance and recovery, this stuff is critical. The material really emphasizes understanding recovery models. What are the key differences between simple, full, and bulk logged?
Yeah, this is fundamental DBA knowledge.
Yeah.
The recovery model dictates how transactions are logged and what kind of restore options you have. Simple recovery basically logs transactions minimally, just enough to ensure database consistency, but it truncates the log automatically after checkpoints. This means you cannot do point-in-time recovery. You can only restore to the time of your last full or differential backup. It uses the least log space.
Okay, simple is simple, limited recovery.
Right. Full recovery logs everything. Every single transaction detail goes into the transaction log. This allows for the most flexible recovery options, including restoring to a specific point in time, like right before someone accidentally deleted a table, but it means your transaction log will grow continuously until you explicitly back it up. You must back up the transaction log regularly in full recovery model.
Full gives full control, but needs log backups.
Exactly. And then bulk logged is kind of a hybrid. It works like full for most operations, but for certain bulk operations like bulk loading data or index rebuilds, it logs them minimally to save log space and improve performance. The trade-off is that if you need to do a point-in-time restore, and that point falls within a minimally logged operation, you might only be able to restore the whole transaction log backup, not to a specific point within it during that bulk op.
Ah, so a slight compromise for bulk speed. Choosing the right model seems critical then.
Absolutely. It depends on your recovery needs, RPO recovery point objective, and tolerance for data loss.
And speaking of recovery, there's that critical mantra, the material repeats.
Oh yes, backups are worthless, restores are priceless.
Why is that distinction so important?
Because having a backup file sitting on disk gives you a false sense of security. The only thing that matters is whether you can actually restore that backup successfully when you need it most during an actual disaster or data loss event. This mantra really underscores the absolute necessity of performing regular testing of your backup and restore strategy as a fire drill. You have to practice restoring your backups to know your process works, the media isn't corrupt, and you can meet your recovery time objectives, RTO.
Don't just assume the backups are good, prove they are by restoring them. Makes perfect sense.
It's non-negotiable for any serious DBA.
Okay, and beyond just backups and restores, what about ongoing database health checks?
Right, proactive maintenance. The material mentions dbcccheckdb, which is the command you run to check the logical and physical integrity of your entire database looking for corruption. Running this regularly is crucial.
Finding problems before they become disasters.
Exactly. And then there's index maintenance. Over time, as data is inserted, updated, and deleted, indexes can become fragmented, meaning the logical order doesn't match the physical order anymore, which hurts performance. So you need to periodically either reorganize indexes, which is less disruptive, kind of like defragging, or rebuild them, which drops and recreates the index, usually more effective but more impactful.
Keeping those index pointers tidy.
Yep. And the good news is SQL Server provides the maintenance plan wizard in Management Studio. It's a graphical tool that lets you easily schedule common maintenance tasks like backups, integrity checks, index maintenance, and statistics updates without having to write complex scripts yourself. Very handy for automating these routine but critical jobs.
Streamlining the essentials. Okay, let's talk about keeping the database available. High availability, or HA. SQL Server 2012 has several options. Let's start with log shipping. How did that work?
Log shipping is described in the material as a pretty robust and reliable solution, primarily for disaster recovery, DR, though it can provide some HA. It works by automating the process of backing up the transaction log on the primary server, copying that backup file across the network, even over the internet, to one or more secondary servers, and then restoring that log backup on the secondaries.
So the secondaries are always trailing just behind the primary.
Right. They're kept in a warm standby state, maybe minutes or hours behind, depending on how often you ship the logs. The main drawback highlighted is that if the primary fails, the role change is a manual process. A DBA has to intervene to bring the secondary online and redirect applications.
Okay, solid DR, but manual failover. What about database mirroring?
Mirroring was kind of the next step up, offering higher availability specifically at the database level. Think of it as continuous, near real-time log shipping for a single database to a single secondary server, a 1.1 ratio.
One primary, one mirror.
Exactly. And it had two main operating modes. High safety mode was synchronous. Transactions had to be hardened on both the principal and the mirror server's log before being committed on the principal. This guarantees zero data loss on failover. And if you added a third server, called a witness, you could get automatic failover.
Ah, automatic failover sounds good.
It is, but the synchronous commit adds latency to transactions on the primary. So the alternative was high-performance mode. This was asynchronous. The primary commits transactions without waiting for the mirror, sending log records over when it can. This gives better performance on the primary.
What?
But there's a risk of data loss if the primary fails before unsent log records reach the mirror. And automatic failover is not possible in high-performance mode. It's always a manual failover, often called forcing service, with possible data loss.
Trade-offs as always, performance versus safety.
Exactly. Mirroring was good, but it was per database, and the secondary wasn't readable, except for snapshots.
Which leads us to the big one for SQL Server 2012. What was considered the next evolution of mirroring technologies?
That would absolutely be always-on availability groups. This was a major new feature in SQL Server 2012 Enterprise Edition, really building on the concepts of mirroring, but making them much more flexible and powerful.
How so? What were the key advantages?
Several big ones. First, you could have multiple readable secondary copies, replicas, up to 4 secondaries in 2012. These secondaries could be used for read-only reporting workloads or even for running backups, offloading that work from your primary production server. That was huge.
Wow, active secondaries, that's a big deal.
Huge. Second, availability groups allow you to group multiple databases together so that in the event of failure, they will fail over together as a single unit. This is crucial for applications that depend on multiple databases being consistent with each other. Mirroring was only per database.
Application-level failover.
Exactly. You define an availability group containing, say, the 3 databases your application uses. And if the primary replica fails, all 3 databases fail over seamlessly to a secondary replica together. It combined the HA benefits of mirroring with the DR capabilities of log shipping and added read capabilities and multi-database failover, a really significant enhancement.
That sounds like a massive step forward for managing critical systems. So with all these complex systems running, how do we keep an eye on them? How do we monitor performance and troubleshoot problems?
Right, monitoring is key. The material highlights an important shift happening around SQL Server 2012. The older tool, SQL Server Profiler, which many DBAs use to trace events.
Yeah, I remember Profiler. Could be heavy.
It could be very heavy on production systems. It was being replaced by a newer, much more lightweight and scalable framework called Extended Events, often called X Events. Extended Events was designed from the ground up for minimum overhead and scalability, allowing you to capture much more detailed diagnostic information with far less performance impact on your production servers. It became the preferred tracing mechanism going forward.
Lighter, faster tracing. Good. What about finding bottlenecks? Where is SQL Server spending its time waiting?
That's where wait statistics come in. SQL Server keeps internal counters that track why execution threads had to wait. You can query dynamic management views, DMVs, like sys.dmus wait stats for cumulative waits in startup, and sys.dmus waiting tasks for currently waiting tasks.
What kind of waits might you see?
All sorts. You might see LCK waits, indicating time spent waiting for locks held by other sessions, a sign of blocking. You might see page latch waits, meaning it's waiting for data pages to be read from disk into memory, an I/O bottleneck. Or write log waits, indicating waits for transaction log records to be flushed to disk, often points to slow log drive performance. Analyzing these waits gives you direct clues about where your performance bottlenecks really are. It's a fundamental troubleshooting technique.
Following the waits to find the problem makes sense. And finally, the material covers trapping data changes over time. 2 features are mentioned, change tracking and change data capture. How do they differ?
They both track changes, but in different ways and with different capabilities. Change tracking CT is the simpler, more lightweight option. Crucially, it's available in all editions of SQL Server, even the free Express edition.
Okay, so accessible to everyone. What does it do?
It simply records in an internal table the primary key values of the rows that are modified, along with some metadata about the type of change, insert, update, delete, and the version. It tells you that a row changed, but not what the data change was or how many times it changed. You typically query CT functions to get a list of keys that changed since your last synchronization. Then you go back to the base table to get the current data for those keys.
So just the what changed, not the how.
Right. Change data capture. CDC, on the other hand, is the more powerful heavyweight solution. It was only available in Enterprise Edition in SQL Server 2012.
Enterprise only. Okay. What does CDC do differently?
CDC works by asynchronously reading the transaction log. It captures the actual data changes, inserts, deletes, and the before-after values for updates, and stores this historical change data in separate change tables. It organizes these changes by the log sequence number, LSN, giving you a reliable, ordered history of modifications.
So it captures the full history of the data changes.
Exactly. It's often used for feeding data warehouses or for complex auditing scenarios where you need that detailed historical change information. It requires more setup and storage, but provides much richer change data than change tracking. It's a key enabler for sophisticated ETL processes.
Wow. We've really covered a massive amount of ground on SQL Server 2012 today. From, those core design principles and digging into T-SQL details, all the way to advanced HA, like availability groups and performance tuning with wait stats and extended events. It really was a comprehensive source.
We really have. And I think the key takeaways from this material are pretty clear. First, prioritize that smart database design. It really is the foundation. Second, think and code using set-based operations for efficiency. Third, test your restores. That mantra, backups are worthless, restores are priceless, is absolutely golden.
Cannot emphasize that enough.
No. And finally, understand the evolving landscape of high availability, especially the power that always-in availability groups brought to the table in 2012.
It's truly fascinating how much of this foundational database, knowledge design, transactions, recovery, remains so relevant even as the specific technologies evolve year after year.
Absolutely. The core principles endure.
And, as you think about the declarative nature of SQL, where you tell the database what you want, not maybe here's a provocative thought to leave you with, how might a deeper understanding of what that query optimizer is actually doing behind the scenes, how might that insight transform the way you approach database design and query writing in your own work? Not just tweaking queries, but fundamentally designing systems that help the optimizer help you, leading to systems that don't just function, but truly perform, even beyond SQL Server 2012.
That's a great question. Thinking with the optimizer. Definitely something to chew on.